Hi again, and welcome back to this third and last part of Lecture 8. This is a rather short one in which we will dip our toes into the topic of the ISM of early type galaxies. The ISM of early type galaxies is hot and diffuse, as we have talked about before. It is largely ionized, and it has temperatures of between 10 to the 6 and 10 to the 7 Kelvin. So orders of magnitude hotter than it is in star-forming galaxies, right? So it also means that this is largely ionized gas. It means that there are other radiation and cooling processes that are dominating the emission from the ISM in these galaxies compared to the star-forming galaxies. The three main processes of cooling and radiation, and remember, as we talked about in an earlier lecture, that cooling and radiation are basically the same thing, right? Because radiation carries energy out of the system, which will lead to cooling. Anyway, the three main radiation or cooling processes are first free emission, which we see here, which means scattering between free electrons and ions, also known as by the German word Bremsstrahlung. That is, basically it means that the electrons are free and ionized both before and after the emission of a photon. And this, it will typically, not always, but typically emit in X-ray. There's also kinds of free emission which emits in radio waves and basically all other parts of the electromagnetic spectrum. You have probably all seen a synchrotron in action sometime during your careers as physics students, and that is basically the same fundamental mechanism that drives any kind of free emission. Then there is free bound emission, which means that, basically that means recombination, right? It means that the electron starts as free and ends up as bound. Free and free bound emission have this thing in common, of course, that it can have any given wavelength, right? Because the energy difference between the energy before and the energy after can basically take on any value. It is not bound to individual steps, such as when it's inside between energy levels in an atom. And finally, there's emission from collisionally excited high ionized metal species. Obviously, this will only be in metals because we cannot have any kind of bound emission in oxygen or in hydrogen atoms. Using the so-called cooling curve, which is defined as the emissivity per ion per electron at frequency nu, we can estimate the hot gas luminosity at a frequency nu as this formula that we have here. I will recommend that you take a look into the textbook of the course in order to see the derivations and so on of this formula. The important part to take away from this is that at temperatures about 10 to the 7 Kelvin and above, this cooling curve here basically only depends on the temperature, and the emission is in X-rays, which are optically thin. So just like we could with the 21 centimeter emission from neutral hydrogen, here in the opposite end of the spectrum, we can also use the X-ray emission from this free emission to determine the mass of the mass of the gas. And we can also use it to determine the temperature of the gas. So yeah, we can use that to directly infer the gas mass, and this has actually led to quite strong evidence for the existence of dark matter. Perhaps one of the strongest pieces, like individual pieces of evidence. And it goes like this. What we're looking at here is the so-called bullet cluster. The bullet cluster is actually two clusters two colliding galaxy clusters. We see one sit over here and we see one sit here. And these have collided, like gone through each other and are now on the way away from each other. But as you can see, the red gas here is the hot X-ray gas from the hot gas in these galaxies. And unlike dark matter particles and stars, even hot and very, very, what's it called, sparse gas, not dense gas, will still be colliding at such rates that it strongly impacts the kinematics on the scale of the entire cloud. So basically, we see that the two clouds have collided, and they sit in the area that we see here. And we know that this thin ionized gas in galaxy clusters makes up more than 90% of the baryonic mass in these clusters. But we can also see something else. We can use gravitational lensing to map where the main mass in these clusters is. We are going to come back to that in a later lecture. But basically, the blue coloring that you see here is reflective of the mass distribution, like the absolute mass distribution of each cluster as inferred from gravitational lensing. And what we can see is that the mass sits here, but the majority of the baryonic mass sits here, but the baryonic mass barely has any impact on the gravitational lensing, meaning that the mass in this pair of clusters is not dominated by the baryonic mass. It is dominated by something else, and that is one of the main arguments for why most astrophysicists believe in what we would call particle cold dark matter. That was it for this one. Now we only have left the discussion questions for this session. And these are question A. Discuss different formation scenarios of elliptical galaxies. Try to identify possible problems of the scenarios you discuss. How would you go about to get an observational confirmation of the various hypotheses you could look at? And question B, early type galaxies contain a lot of hot gas. Where do you think this gas comes from, and what processes have made it hot? Where do you think cooling is most efficient in elliptical galaxies? And that was it for this time. Thank you so much for staying with me this far, and I will see you in the next one. Bye for now.